now continue with our property of the water plane area. Let me draw once more this water plane area. Now, this time I should be correct. This is my xx, this is my y. See, I also require to calculate I about the transverse axis. Now there is a important point. This is my center of flotation. Actually, I will require to find out I about a transverse axis going through this. Okay, but there is no straightforward way to do that initially because I don't know this distance yet. This is my LCF. What we do is that we will find out I about my this y axis first. What is that value? Again, if you take a small chunk here, this is my y, this is my dx, this is my x. So it is integration of y dx into x square into 2 because there is twice that area there. See this y here, this y here, this y this side because this is only half water plane. This is y, there will be another y because the actual shape is like this 2y dx x square. So this is the integration I need to do. So it is 2 x square y dx over the length. But this is actually yy. Again, see, moment of inertia is area into distance square. The area is here y dx into distance is x. This is my x. X square. No, not twice x square. But my area is actually 2y dx. So that's why there is a 2 here because it is symmetric. It is both sides there. But this is yy about this line. And I then yy through f. There is a simple formula of parallel axis theorem. See, it says that this is given by Iyy minus area of water plane into xf square. This is called a parallel axis theorem, that if you have like any body here about any axis, if you want to find out I here, and if you want to shift it parallelly through an axis through its centroid G, then it is given by I of that is I of this minus area into distance square. See, I through G is any I minus area into distance square. This is the standard formula given. So in here I found I about this axis, which I can easily find out. Now I have to translate and find I about this axis. So I have to shift it by a distance LCF, and always I about its centroid is a minimum. Therefore, I about this is less than I of that. That's why it is minus AW into XF square. Now you see, this I calculated earlier, already there, because in the first slide under the water plane I did this calculation. This also is calculated. So in the same table I can actually calculate all of them, which I will show afterwards. But this is my IYF. Again, some people call it IL or I longitudinal, which is again a misnomer. You see, people call it like this. I will tell you why it is called in a minute when we talk about the terms that comes in. Just 1 second, then I will. Okay. Now let us see where these terms come in. Okay, where these terms AWP. I mean, we have calculated then area AWP, LCF or x of f. We calculate I x or IT and IYY through f or IL through f. I am writing this f to indicate that it is through center of flotation. We have calculated this 4 thing, this and this. Where does it fit in? And how do I represent that in hydrostatic calculation? What happens is that there is a term called tons per centimeter of immersion. This is called TPC. This we will find out the use of all these terms afterwards when we do the actual calculation. But right now I will tell you that TPC becomes equal to rho into area of water plane divided by 100. Basically it means how much tons you require in order to sink the ship by 1 centimeter, or how much tons you require to remove for the ship to come up by 1 centimeter. This is TPC. So I calculate this, therefore it comes in directly here. Okay. LCF or XF has its own value. This will always be necessary directly. We will need this for a plot directly afterwards. IXX and IT. Now there is a very important term called BMT, which I will explain afterwards, but this term, this is called transverse metacenter. This is center of buoyancy. The distance between center of buoyancy and transverse metacenter. This is given by I T by V. Actually, it is I X X by V. But you see, this is why IT is used. In fact, this term will occur when we do study transverse stability. Okay, at that time this term comes in, and we will find out that geometrically it is something like that. If there is a ship here, this point called kill point, this is a kill point, there is a center of buoyancy here, and there is a metacenter here, and this distance, when I write BMT, some people write with a bar here, it means distance from B to MT. That's what it means, point B to point MT. That is the distance. The significance of that will be clear in a later lecture, but this is an extremely important quantity. We call that, this is given by IT by V. Now this we calculate here, and this of course we had beforehand. Okay, this is how we call that. This is by itself done. Now comes other one. One more term is there, BML. This will be given as IL by V or IYY through F by V, through F we should write. But BML is of no direct use, generally speaking. What happens is that there is a term called moment to change stream by 1 centimeter, or MCT. Some people write that way. This is given by weight into G. Now I will write that, I mean full form, then I will L. This is LBP, which is written as weight is W, okay, into BML by 100 LBP. Now weight is actually rho into displacement. No, sorry, not rho. Rho into volume is the mass into G. I will explain that in a minute, by 100 LBP. This is my volume. This is my, supposed to be my, no, G is gravitational acceleration. Now this is this term I must explain again. No, I have got this MCT as rho this into BML by 100 LBP. This terms requires little explanation once more. See, what happened is that MCT means moment to change stream by 1 centimeter. Okay, it is a moment causing to change stream. Now what is a moment? Moment is a force into distance. Moment is force into distance. Okay, what is the unit of force and distance? Basically, the unit of force is kilonewton, not tons, but kilonewton. Force is kilonewton, distance is meter, so it should be kilonewton meter. Okay, but we sometime want to find out, if I have shifted a weight of 5 ton from here to there, what is my moment, and sometime force is written in terms of tons. Then what happens, if you take is ton meter, then it becomes ton meter. In such cases, most books, what they do, this MCT, it is expressed as a ton meter, and so this G is not there. They will write, or rather I will write this in another piece of paper, that again there is a confusion of this thing. MCT, if you write this way, this will basically become, this unit is tons, this is meter. Okay, so it becomes in ton meter divided by here meter, so it becomes tons. So this becomes total tons. What happened is that this MCT here, basically, if you want to find out quickly how much of ton, if I shifted from here to there, it is going to basically go down by a trim of 1 centimeter, then you end up getting a unit of this ton. In fact, it will become ton meter, because this L takes care of for the trim part. But please remember that in many calculations, moment would be better represented by using kilonewton into meter. See, we have this persistent confusion of force being expressed sometime as tons, sometime as kilonewton. Okay, so in all literature, will try to tell us that moment to change trim expressed as ton meter. Remember that ton meter is not strictly an SI unit for moment. An SI, international standard unit for moment, is kilonewton meter, force into distance. Again, moment is force into distance. This is in kilonewton, this is in meter. But if you write moment as tons into distance, I mean like ton meter, remember that this we write sometime, but we are implying here for our calculation, for practical calculation, when we are shifting so much of tons, say 10 tons from point A to point B. See, if I shift a 10 ton of weight from here to, say, by 5 meter, I will tell that I have given 10 into 5 ton meter of moment. You see, I will say that loosely, but actually speaking, the force I gave is 10 into 5 into G kilonewton meter. But we normally call this, most ship people are used to this. Therefore, MCT formula in the hydrostatic calculation do not have G. It is expressed as a ton meter. I wanted to mention this, that moment is necessarily kilonewton meter, but for MCT the moment is expressed as ton meter. So our formula becomes this one, MCT. Okay. Now comes to some more calculations. Now these 4 calculations we have done. So now, okay, let me now plot that. So here we have got again various Z. You are supposed to do all this now. So here you plot AWP. You can plot AWP. Some people don't plot AWP. Some people plot instead of that TPC, because it is going to be just proportion to that. TPC is proportion to AWP. Then you plot XF, that is LCF. LCF is always plotted. Then you will plot, let me see how it might look like, BM. Say you will plot here, say BMT. You may plot here also BML. Normally people don't plot, instead of BML you may plot MCT, something like, say, let us say MCT. It may be not correct, because if BML is this way, MCT should follow that way. Just for illustration purpose, I am saying you plot MCT. See, all this calculation, please remember, has come out from only the integration over the water plane area. Remember that AWP was there directly, TPC was directly AWP divided by 100, MCT is connected to BML, MCT is, volume into BML by 100L, BMT is of course IT by V, LCF is also calculated. Sometime we will calculate also what is called K to MT, which is given by KB plus BMT. What it means is that you had here the kill point, you had here the center of buoyancy, you have here the MT. We basically plotted this. This is also there with us. We have done earlier in my previous calculation. We had displacement, we had volume. If you recall, in the previous one, we had LCB, we had also KB or VCB. We had all this from the previous one. So this, sometime if you add KB with BMT, that is, say at some point KB, this KB value with BMT value, you get KMT. So you can plot KMT also. Say this is KMT. Against draft. All these are against draft. This is draft. These are all various scales. See, what happens is that these are all for different scale. I will show that in next curve. All these plots are having different scales. That means it will say that 1 centimeter equal to so much ton meter, 1 centimeter is so much meter cube, etc., etc. So that what happens that if you have this curve, now if the ship is lying at this line, you can pick up all the values for that line. Say there is a ship there, you go and mark that, see the ship is having a draft of 8 meter. So for 8 meter, you can find out all its properties. What is my displacement? What is my center of buoyancy? What is my longitudinal center of flotation? BMT, KB, all these quantities. In addition to this, you also plot in hydrostatic, this Professor Bhatt would have covered, all the form coefficients. That is CB, CW, C midship, CP. This also you plot on that, because they are all already done, because these things are all connected to displacement, area of water plane and area of midship. Midship area is available from Bonjean's. This is available from Bonjean's. Bonjean curve you have done for each section, areas up to each line. So this is available for you from Bonjean. This is already available here, AWP. This is available also here, this. So all these things can be easily calculated, because CV equal to displacement by LB into T. This equal to AWP by L into B, etc., etc. So all these you plot them. This set of curve, that is, now I will summarize that what all hydrostatic, therefore this thing. Therefore the set of curve of Z versus, let us count one by one. Volume, displacement fresh water, displacement salt water, okay, VCB, LCB. This takes care of actually volume and its centroid. This is connected to volume and its centroid, all, okay. Then AWP, TPC, these two are connected to AWP. Then LCF, then BMT and KMT. Okay, these two are related because this is nothing but this plus VCB. Then BML, actually sometimes similar way you can do KML and MCT. These are all interconnected. BML into rho V by 100L gives you MCT. KML is BML plus KB or VCB. See, this is nothing but, see, KML is from kill to metacentric height. That is killed to center of buoyancy plus center of buoyancy to metacentric height. So this is there. Then form coefficients are there. That is your CB, CW, CM, CP. Okay. All these things, when you plot in a curve, there can be some more. Some people will have some more. Like sometime what we mentioned is weighted section area. That is weighted hull area. This I will come little later on because there is no direct way of calculating this right now. All this when you plot against Z, this is called hydrostatic. These are called hydrostatic curves. One of the most fundamental set of curves that you have for any ship during design. When it is designed, there must be multiple copies of that all over the ship with a captain here, there, etc. because it becomes extremely useful for any decision whatsoever. You want to think that I have to load so much of tons of cargo in hole number 5, you have to find out hydrostatic to figure out if you do what will happen, what will be the draft forward, what will the draft up, will it remain stable, will it become unstable. If you want to know, say there's a deck crane, you want to lift a weight, you have to study whether vessel will become unstable or stable if you just lift a weight. Sometime it happens unstable. Like that, all calculations and decisions will be depending on this set of curves, which is extremely useful or extremely necessary for us as we go along. Okay. So this, you see the number of them up there, but if you recall, the integration that we did was not so many. The number of integration that we had, I want to this write again. Was basically one integration over length of section areas, one integration of section vertical moment of section areas, one integration of x into section area dx, then this is section area. In one table you could do this 3 for any draft. Now other one was water plane area, longitudinal moment of water plane area, this, and that's all. 1, 2, 3, 4, 5, 6, 7. People think that there are so much calculation, but actual integration, if you systematize it, is only 7 of them. This 3 comes on one table, this 4 comes on one table. This 4 I will discuss in a minute because there was some little doubt. This 4 comes on one table. So you see, only thing is that you have to do that for various level. You have to do that for repeat it, yeah, different Z's or water lines. That's the only thing. And nowadays it is done very systematically in a computer. Everybody does in a computer. Like it's a PC based. You can do. It'll take maybe a split second to run the program. The number of computations are so less that it will take only a very small time to do the actual calculation of hydrostatics. But hydrostatics is one of the most important set of calculation that we can ever have and most fundamental. This is exactly why I wanted to tell about the integration rules which we have discussed earlier. Now again here what I will do is that I will show in one table how we can carry out these integrations once more, just to show, because we had some little once you get a hang of that, we can always get this thing clearly. Again here I will try to show there that when you do the integration, x is always written as n into h. N is the station number, h is station spacing. Now if you, therefore this calculation you can replace that by this, you see. So let us see how we carry out this calculation in one piece of paper once more. So I had here This time I'm going to write slightly small because it is not otherwise fitting in a piece of paper, you see. Then x y dx is equal to n y dx multiplied by h, because x is hn. The next one is y cube dx, it stays like that. Next one is x square y dx is equal to h square n square y dx. Okay, this is what we are doing. Now remember that these are the four quantities we have to do. Now I'll as I said, I'm going to write little small here, otherwise piece does not come in. So I had here n, first column. Okay, then I am going to have here y. This is given to me. Remember, this is will fill it up. Then I will write here weights. I am writing this as weight, or some people call it Simpson's multiplier. This is weight or Simpson's multiplier. Okay. Now we will let me fill up little bit of some of these numbers. So this is 0, 1, 2, like that it goes to, let us say 10. So I have got this number, say this is 0, this is 0.5, something, say this is 1.8, like that. Some numbers are there. This is 1, 4, 2, 4, like that, like 1. This is little small. My writing is small because I have to cover a lot, as I said. Next one is going to be W into Y. Okay, let me fill the numbers little bit, then we'll know. W into Y is this into this. We go, so this is 1, this is 2, this is say 2 into 1.8 is 3.6, like that. Oh, sorry, first one is 0. Yes, first one is 0. Okay, now at this point I am going to add this up. Say this gets some number, let me call this to be A. So what happened is that then my area becomes H by 3 into A. I mean, this sum part I am calling A. Okay, this gives my AWP. So this is over. So that is, this part is over. This integration turns out to be equal to this. Okay, we are going carefully again. N is 0, 1, 2, like that. Y is 0 0.5, 1.8, like that. W is 14241, whatever rule we are using. So y into W is my, basically people call it the function of ordinates. So it is this. Area is this. You can multiply by twice afterwards, but this quantity is this quantity. AWP is going to be twice of this because it is 2y dx, since y is on both sides. That I will come later on. Now let us come to this one. What we should do? My ordinate is here x, y. This is my ordinate. Remember, as I said, this is my ordinate. So x, y is essentially ny. So basically I replace that with n. That means I am doing this into this. So this is, let me take another color here, multiplication of this column with this column. That means it is 0, this is 0.5, this is 3.6, okay, like this. Now I have to multiply this column, that is ny into W, because I am integrating this column. So I have to multiply this column with this W. Okay, again, see, this is my ordinate. See, we will go one by one. This was my column I want to integrate. Then I multiply this with weight. If I want to integrate this, then I multiply this with the weight and add that up. That becomes my ordinate. Now I want to integrate ny. So my y must be replaced by ny. This column must be replaced by ny. That is here. I am replacing it. Okay. My y must be replaced by ny. So I am writing another column of ny here. This is the column. Then obviously I have to multiply this with w. So if I multiply that with w, I am going to get here. See, I am multiplying this column with this column, this 2. So I am getting 0 here. Then this is 2 here. This is going to be 7.2, like that. So it's point by point integration. Y was to be integrated, so this was multiplied with the weight. Now I have to integrate this column, so I have to multiply this with weight. I have to integrate this column. Remember, the ordinate and the curve under which I want to integrate is given by ny. So ny is these values, these numbers. So this multiplied by w gives me this. So this I add up, I get, let us say this is L, I call it. Okay. Then I will come to this expression by integration of ny dx given by h by 3 of L. But if I multiply one h here, then I have got one h square here. See, ny dx is h by 3 L, but I have to do another h here. So h ny dx gives me this. So I multiply with an h here. Okay. You will see the units also afterwards. See, this has no unit. Let us check the units if there is a confusion. This has no unit. This is having no, it's not meter anything. Y is a meter. So these are all meters. So this quantity is a meter. In meter. So this is in meter. So this is meter. A is in meter. H is in meter. So this into this gives me meter square. So area is meter square matched. Moment should be meter cube. Now you see ny is what? Meter. So ny into w is also meter. So this is my meter. So meter into meter square. That's my meter cube. So if you did not take this h square, you would have got here meter square unit, which is wrong. This is why you have to multiply with h square. Even if you have, if somebody has forgotten or mistaken, you can check the dimension, it will come out. Now we'll come to the next one. Next one is y cube. So now you see, you have to replace this y by y cube. So I simply write y cube here. Y cube is going to be here 0. 0.5 cube is going to be 0.25 into 0.5 is maybe 125. This I cannot, we have to calculate whatever. Okay, see, you are cubing this. The ordinates are now y is replaced by y cube. So 0 is 0, 0.5 is 0.5 cube, that is 0.125. This will become 1.8 cube, like that. Once more multiply that with this into y cube. Okay, that is this into y cube, this into y cube. This is 0. This is 4 times 0.125 gives you 0.5. This is 2 times this, give you say 2 into 1.8 cube. Okay, like that you are adding it up here, you end up getting, let us say I am calling this to be IT, because it is going to be proportional to that. Now it is integration y cube dx integration. Remember, there is no h and all, this is the correct number, so it becomes simply h by 3 into IT, this number. Check the unit. What should have been the unit of this? It should have been actually meter 4, because it is meter cube in the meter 4. So here you see, this is meter cube, because y is in meter, so y cube is meter cube. W is no unit, so it is basically 0. Sorry, it is also meter cube. So IT is meter cube. This is meter cube multiplied by meter. give you meter power of 4. So it is also correct. In fact, this is a more easier one. Now I'll continue this way. Now comes this x square y dx. This is the most confusing one sometime. Now x square y dx is actually h square n square y dx. So I have to now take the ordinate as this n square y, n square into y. So this becomes my first one 0. Second one is 1 square into 0.5 is 0.5. Third one is 2 square into 1.8. See, 2 square is 4. 4 into 1.8 7.2. Like that we have done it. So the ordinate, this is my ordinate. Remember that this is my ordinate. This number is my ordinate. This is n square. We are not able to write here, but this is n square y. This is n square y. This number is n square y. Let me see this way. It is n square y. This column. Once more, how it is n square y? N is 0, y is 0. So square of this into this is this column. Because I am integrating that. I am trying to integrate n square y dx. Square of this is 1 into 0.5. That's 0.5. Square of 2, 4 into 1.8, 7.2. This way. This is the column I want to integrate. So I multiply this with w. Simpson's multiply. Now what 1 into 0 gives me, this is now, I will write this way because there is no space, w into n square y. This gives me 0. This is 4 times 0.5 gives me 2. 2 times 7.2 gives me 14. I don't know whether this is right or not. This may not be right. Sorry. This okay. This is right. 14.4. Like that I end up getting. So this now when I do, I add, I get say IL. Okay. And now remember that this is where the confusion will come. N square y dx. This is n is equal to h by 3 into IL. But I have an h square multiplied here. So I have to multiply h square. So this gives h cube by 3. This is very important. Now let's check again the units. What is the unit of n square y? It is meter. So I have got this thing as meter. So this is meter. Meter cube gives me meter 4. So this checks out. Okay. So all this integration has now checked out for us. This is in meter, meter square, meter cube, meter cube. Now having done that, then it is only question of one line. Just one line we can find out all these things. Then you see AWP, I will say, is twice of this integration. So I have got this number. I have got this number earlier, just multiply twice, you get this so many meter square. Then LCF. Here you see there is an interesting part. LCF is supposed to be the longitudinal moment of the area divided by AWP. So if you take 2 twice, 2 gets cancelled out. So it can, you can write this to be x y dx divided by y dx. Remember that this is not area but half the area, but this is also moment for the half area. So if you don't like it, you multiply 2 and cancel out 2. I mean, you can write 2 2 and take it out 2 2. It does not really matter. So you will get something in meter. Straightforward. Then I transverse, I mean T or Ixx is integration of the last part we are doing x square y dx, actually into 2, because this is for half the part. Remember that this is for half the part and I have to have another half the part. So I got this number is so many meter cube, no problem. Then IL is equal to okay, actually here again I call this IL as Ixx. See that's where that confusion comes here. This IL here has turned out to be this, but does not matter. This IL is IYY. This is our IL is 2 by 3. I believe that is the formula, y cube dx. This is through the axis. Okay. So this I have found out earlier. Remember there is not 2 here. Remember there, you don't, unlike here this 2, there is not 2 here. only this part you have to take into 2 by 3, the full thing into 2 by 3. So you should not multiply this area what I have done before with 2 already. We have to carefully go that this term into 2 by 3. So I get something meter 4. Now I have to get IL through F. This is actually this IL, that is this value, minus LCF, which I have already calculated, square into AWP. So this I have already done here. This I have already done. This I have already done here. This I have done here. So all these are available. So one table I have got all quantities. In one table, therefore, I have got all these quantities of AWP, LCF, IT, IL, and whatever I want. Then after that, of course, is only question of one line to find out BM T equal to IT by V. There's just one line. Then BM L equal to IL by V, etc., etc. These are all just one line number calculation. There is no calculation involved as such. Okay. Now, having said that, sometime there are some small things that are also added in a hydrostatic calculation. Is something like this. See, you have been talked about molded, breadth, etc. The word molded has been taught earlier when you have this dimension taken up to outside or inside. So what happens is that the offset that we get is for inside values. Okay. So whatever I have got displacement is basically for molded displacement. What we have got is we got molded. This column is, I should not take this, molded displacement. But you may, that means you have got this value. Sometimes you may want to get the extreme displacement. Now, what is the difference? The difference is the volume of the thin plate here. Now, there is no formula for that. Normally, what one do is that one multiply this molded with some factor, which may be actually 1.02 or something like that, some factor, or say 0.3, something like that, 2-3%, or maybe smaller than that. I cannot often tell. This is a small factor to get delta extreme. This is a question of, what I mean, a convention. Remember that having done this integrations, the rest of the part is really trivial. All these are just 1 or 2 or 3 multiplications. Just multiply with some numbers to get what you want. But otherwise, what we have got is essentially 7 integrations that I showed earlier per water line. If you could do that, entire hydrostatic calculation is available to you. And then from that it is one line. Somebody wants extreme displacement, you just multiply displacement with some factor. Somebody wants something else, which will be all function of these numbers. Now one more thing that I will do for that is how we represent that in one graph, which I did not mention earlier. See, I just showed schematically. So what normally is done is that we take a now bigger graph. There is normally draft in meter. Basically it is Z, as we know. Let us say how we represent. See, there, let us say this volume. My volume would normally go like this. What does it mean? Now you write here, this is volume. Then you say 1 centimeter equal to, let us say, 1000 meter cube as a scale. That means if this is to be your, say, 10 centimeter, then it will be 10,000 meter cube. So you have to write along the length the scale. Normally I wrote this way, but people will write along the length, because this is supposed to be in meter cube. Now displacement here, this you will write here 1 centimeter equal to 1 ton, something like that. or 1000 ton, no, not 1 ton, 1000 ton. So that in other words, each quantity, it's a very complicated curve in the sense that I am representing some 10 or 15 or 20 curves, but each are different. Some is meter cube, some is no dimension, some is meter, meter 4, something like that. See BML. So suppose I have got say BML. I will write here 1 centimeter equal to say 10 meter, because it is a measure of, I mean I have put them in that particular scale. CB, no scale because it is having no unit. Like that, each quantity, the scales must be mentioned, because without that it is like a graph you cannot read. You see, you cannot make anything out of it. So the scales are absolutely essential. You will have to write clearly, and since it is number of curves, normally one writes along the length. You see, because there will be number of graphs coming in one sheet, so one will write basically along the length how do you sort of what scale you have used. Now the beauty of this curve, of course, as I said, ultimately is that suppose now you have the graph and you know the ship is actually lying at this level, which may not be the calculated point. The calculated point was this, calculated point was this. You can easily go to the plot and measure by put a scale, measure that, and tell me that okay, that means the ship's volume is so much of meter cube. So I will know all the hydrostatic characteristics of the hull for this for a given draft. The only problem is that this is normally for even keel, because what we have done is that, see, that we have got a ship here. I am writing in a very, we assume that okay, what will be the property if it is under 1 meter water line, what if it is under 2 meter water line, what under 3 meter water line. We have not done the calculation for trim. We really cannot do it because there is numerous variation. You really don't know, you cannot do for every possible line. So normally you are doing for say drafts at 1 meter interval at higher level, maybe at half meter at the lower level. Okay, at the lower level you may do half a meter interval, at higher level 1 meter interval up to upper deck. Normally you do that. This is what you do. Okay, you don't do for trim because there is no like end to it. What, how much trim will you take? That we will find out in subsequent lecture, how from the hydrostatic particulars we could calculate things for trimmed condition also. That means when I put a weight, it sort of trims, how I could find out. So hydrostatic therefore becomes, I can write this, that hydrostatic becomes the most fundamental property, geometric characteristic of a hull. Rather R, or rather I say represent, that's a better word perhaps. So hydrostatic represent the most fundamental geometric characteristic of the hull, in the sense that from the hydrostatic you could find out if the hull is submerged up to a certain level, all its properties as related to hydrostatic pressure. This sometimes we don't say that, but it is connected to hydrostatic pressure, because we will be considering only under steady still water what happens to the ship. So the only pressure is hydrostatic pressure. I think this is where we end the talk today.